Good morning, I am Nicolo Zenoni. First of all, I would like to thank the organizer for the opportunity to present our work. This presentation is based on our paper on subregion action complexity in ADS-free and in the BTZ black hole, whose main research topic is ADS-CFT correspondence, a duality between a theory of gravity in anti-de Sitter spacetime and a conformal field theory on ADS boundary. The feature we are here interested in is that geometric quantities in the bulk spacetime can be related to physical quantities defined in the dual field theory on the spacetime's boundary. For instance, the area of the Ryuta-Kainagi surface in the bulk is related to the entanglement entropy of a state defined in the dual conformal field theory. Among the various applications of ADS-CFT, I will concentrate on the study of a black hole interior, on which nowadays little is known. Since we can put a black hole inside ADS, we can approach this problem in a holographic framework. In this context, it is interesting to find a quantity defined in the dual field theory, which provides us with information about the interior of a black hole. Such a quantity must grow for much longer time than the thermalization scale of the system, just like the Einstein-Rosen bridge inside the black hole does. A good candidate is computational complexity. Complexity can heuristically be defined as quantifying the difficulty in carrying out a task. Given a quantum system, the task will be to bring such a system from a simple reference state to a final state of interest by applying a set of simple operations. Complexity of the final state is defined as the minimum number of simple operations doing this job. 3 conjectures have been proposed for bulk dual complexity, 2 by Leonard Susskind and others, and the third one by Couch and others. According to complexity equals volume, or CV conjecture, complexity of the dual state on the boundary is proportional to the volume of the codimension 1 maximal bulk surface anchored to the boundary time slice, representing here the dual state. According to complexity equals action, or CA conjecture, complexity is related with the gravitational action computed on the Wheeler-DeWitt patch, which is the domain of dependence of the slice involved in CV conjecture. According to complexity equals spacetime volume, or CV 2.0, complexity of the dual state is related to the spacetime volume of the Wheeler-DeWitt patch. These are the proposals for pure state complexity. It is now interesting to extend the notion of complexity to mixed states. As I said, a world time slice on the boundary represents a pure state in the dual field theory. If we consider instead only subregion on the boundary, we are considering mixed state in the dual field theory. The putative bulk dual of complexity of such mixed states can be extended from the pure state one involving the entanglement wedge in the bulk. According to holography, indeed, the entanglement wedge encodes all the information about the density matrix of the dual state on the boundary. Therefore, we have subregion CV proposal, according to which subregion complexity is related to the volume of a maximal codimension 1 bulk surface anchored at the Ryuta-Kainagi surface and the subregion on the boundary itself. According to subregion CA and subregion CV 2.0 instead, subregion complexity is related respectively to the gravitational action and the spacetime volume of the intersection between the Wheeler-DeWitt patch and the entanglement wedge. The first step towards the understanding of which is the bulk dual is to compute this free quantity in different spacetimes, investigating, for example, the divergences, subadditivity or superadditivity properties, and the temperature dependence. Here I will concentrate on ADS-free and BTZ spacetimes. From previous works of other authors, we know that the volume in these spacetimes is a topological quantity. It is interesting to see what is the result for the action and the spacetime volume. Here are some technical details about the computation. In the picture, it is represented the spacetime region of interest given by the intersection between the entanglement wedge in yellow and the Wheeler-DeWitt patch in red for a boundary segment in BTZ spacetime. The ADS-free case is analogous. In order to regularize the result, we introduced a UV cutoff at constant Z to which the Wheeler-DeWitt patch is anchored. Sending the patch from the boundary and cutting it off leads to the same divergences, So we'll concentrate only on this construction here. Well, the gravitational action have many contributions. The first one is the bulk one, given by the Einstein-Hilbert action. For both ADS-free and BTZ spacetimes, we note that the spacetime volume is a welcome gift from the bulk action, while if we want to compute the whole gravitational action involved in CA conjecture, we have also to take into account the boundary terms. In particular, NAR surface contributions can be set to 0 by choosing lambda and a fine geodesy parameter. We still have joint contributions coming at the intersection between two null boundaries. These contain an arbitrary reparametrization constant coming from null normas to the intersecting boundaries A1 and A2. To eliminate such a dependence in the action, we must also consider a contour term for null boundaries, depending on the expansion growth rate theta, at the price of introducing an arbitrary length scale L tilde. Summing up all this contribution, after several simplifications, we get this strikingly simple result for both ADS-free and BTZ spacetimes. In particular, both the action and the spacetime volume present a linear divergence depending on the segment length L, a logarithmic divergence represented by the entanglement entropy S of the dual state, and a finite term containing the CFT central charge C. As we note, the action depends on L tilde, this arbitrary length scale, and here we can only say that L tilde should be greater than the ADS radius in order to have a positive definite subregion complexity, but nothing else here. Given this elegant structure, it is interesting to test if it survives to more complicated subregions. The easier option is to consider two subregions on the boundary of equal length L and distance d. According to the values of L and d, we have two possible configurations for the Ryuta-Kayanagi surface, and we have to choose the shortest one. So, if d is greater than a critical distance d0 proportional to the length L of the segments, we trivially have two replicas of the one segment geometry. So, to get both the action and the spacetime volume, we can trivially double the previous results. If the distance is less than the critical one, we have to build new wedge, new patch, and do all the computation. And in the end, we found the same divergences as before, where S is the entanglement entropy of the two segments, and a finite part, which is a complicated function of L and D. Anyway, these results allow us to investigate superadditivity properties. We can do this by considering mutual complexity, defined as the sum of subregion complexity for two regions, A and B, minus subregion complexity of the union of these two regions. By using the single segments results and the two segments one, we can see that if the distance between the two segments is greater than the critical one, subregion complexity trivially saturates superadditivity, while if the distance is less than the critical one, the spacetime volume is superadditive at all the distances, while the behavior of the action depends on the value of the arbitrary length scale L tilde. In particular, the action is superadditive for all the distance only at large L tilde, as we can see here in the plot on the left. Summarizing, we have seen that subregion complexity is related to the entanglement entropy, but it carries a different amount of information. One of the interesting conjecture backduas, the gravitational action, depends on an arbitrary length scale L tilde, which affects superadditivity properties, and this calls for physical interpretation. In conclusion, we are not able to say which is the bulk dual, and to answer this question, we have to understand complexity in the boundary conformal field theory. Thanks for your attention.